Okay, in section 3.2, we're going to talk about the equation of a line. We're going to compute and interpret the slope, which we actually talked about previously, but do it again. We're going to find and interpret the y-intercept of a line. And we're going to write the equation of a line in slope-intercept form. So the slope, the intercept, equation, and slope-intercept. So, quick recall that the slope, symbolized with an M, not to be confused with the mean, not to be confused with meters, and not to be confused with miles, which is MI actually, is a ratio of change. Okay, and I'm going to write this, the change in the response variable compared to the change in the explanatory variable, and with labels. Labels mattered. And that this, in terms of an equation, so if you're a formula person, the change is the difference in the two values, and similarly, it's the difference in the x values. Okay, not so heavy on the formulas here. Example 1, driving. Few people driving away from Illinois. Who knows what they're doing? They're going up north to a lake. They're going down south to a beach. Who knows? Whatever they're doing. They are driving away from Illinois. They're on the highway using cruise control. It took them 2 hours to go 130 miles. What is the explanatory variable? What is the response variable? And assign them variables. Okay, so let's see. Well, we have two things happening. We have time and we have distance. So does the distance depend on time, or does the time depend on the distance? So I feel like time doesn't really respond to too much. It is usually the explanatory. So the time is explaining how far. So independent, which is the explanatory, time. Let's call this time in hours. And let's assign it a T. Why not? You could call it H for hours, whatever. And the response variable is how far, distance traveled. So response, distance traveled. I don't know. D. Got it. Write 3 ordered pairs that describes the correspondence between the time and the miles in this situation. Write them with the ordering. Explanatory, response. Okay, explanatory was the time, response. So immediately we already have one given to us. Explanatory, 2 hours, response, 130 miles. So 2 and 130. Well, I feel like on cruise control, if you went 0 time on cruise control, then you traveled 0 hours. If we simplify this, this means in 1 hour, what is half of that? Is that 75? Dang. In 1 hour, no, that's not 65. That's better, that's better. 2 65s makes 130. Got it. And you could scale this up. You could go, we could double this. We could go, well, you're cruising along for 4 hours and you end up going 260 miles. There are a lot of ordered pairs that you could write here. But we want it to be explanatory, the time, explains the distance, which is the response. Find the slope of this line. Well, I claim we actually found it. We took the rate, which is 130 miles per 2 hours, And we actually scaled it down one right here to be a unit ratio. We just didn't label it. These ordered pairs are not labeled. But the slope, remember, is the ratio. So the ratio of change in one to the change in other. So the change in the response is 65 miles compared to the change in the explanatory, which is per hour. So slope of this line, 65 miles per hour. What does the slope mean in the context of this situation? Well, we labeled it. Okay, so really maybe we should write it like this. I guess. That's silly. To me, the slope means on cruise control, they travel 65 miles per each hour. Got it. Write an equation that relates miles driven to time passed. Oh. Okay. So our job is to write an equation for this. Well, it seems like if I know that we're traveling 65 miles per hour, and let's say we drive for 0 hours, then we're 0 miles. In 1 hour, we're 65. In 2 hours, we're 65 times 2, which is 130. And then for 4 hours, that was 65 times 4, which was 260. So an equation that relates the miles driven to the time passed. So I'm actually going to write this without creating my pattern, but just to write the pattern, because I like doing that too. T and D. At T0, there was 0. At T1, 65. At T2, 130. At T3, oh, we did not. What is the constant increase here? Plus 65. So what, 195, and then add to that 65, and we would be at 260? Yep. Okay, so it looks like there's no initial, but we are at just 65 times the amount of time. So the distance is equal to 65 times however many hours, where T is in hours and D is in distance traveled. All right. Cheap seats. Let's look at the cheap seats. The price of a ticket was originally $1 in the year 2010. Its price has been getting more expensive at the rate of 50 cents per year. Make a table of values to keep track of the cost of the ticket since the year 2010. Okay, so, and then it says graph it using your calculator. Ooh, very interesting. Okay, so let's see. Right, so we're going to have time. Is time in years? Yes, time in years after 2010. So years since 2010, and ticket price? Ticket price in dollars. Okay, in 2010 it was $1. $1. In 2011, increased by 50 cents. Got it. In 2012, increased by 50 cents again. Now it's at $2. 2013, $2.50. 2014, $3. Okay, got it. Then graph this situation using your calculator. Okay, well, it looks to me like we are going to have a list 1 and a list 2. We're actually going to create a scatter plot. So, here here we go. Let's see. So now we go Stat, Edit, and I have a ton of data in here. So I'm clearing it. And in list 1, I'm going to put 0, 1, 2, 3, 4. Did we go up to 4? We sure did. And in list 2, I'm going to put $1, $1.50, $2, $2.50, $3. Okay. And now I'm going to go second stat plot, and I'm going to hit enter. I'm going to turn on my statistics plot. I have to zoom in here because of the glow. And the type that I'm going to pick is this one with just dots for my coordinate pairs. My X list is L1. It is the year since 2010. My Y list was the ticket price. That's what I entered into there. And now I am going to go to Zoom and down to Zoom Stat. Enter. Okay, and so this is what we get as our image. Okay. All right, so I noticed that we can't see the bottom axis, which is fine. So looks to me, so just to see this window, okay, oh man, that's awkward. Starting at negative 0.4 and it's counting by ones. If it's starting at negative 0.4, hold on. Let's go, oh, Y minimum, 0.66. Okay, back to the graph. So this must be 1, 1.5, 2, or no? What is it going up by? One more time. The Y scale is going up by ones. Okay, so I see 1, 2, 3. This is 1, this is 2, this is 3. And I notice, oh, I see it's going up by 50 cents each year. Got it. And this would be 2010, 2011, 2012, 2013. Got it. Okay, very good. So it said, graph this situation using your calculator. Okay. So just so that we get all of that information, it went 1, 2, 3, and at 0, at t equals 0, at the 0 hour, that is 2010. So this label, this is money. Cost of ticket. And this is years since 2010. Okay. Let's see, let's go. All right. $1, and then we saw this happening. Wait a minute. 1 above 50. 2 years later, $2. 3 years later, $2.50. 4 years later, $3. Okay. And that's what we saw on our scatter plot. Is this a linear model? Yeah. How can we tell? Well, there's two things that clearly show us. First, this looks like a straight line. Okay, so right off the bat, yes. Looks pretty linear. Okay, and then there's another way to tell, and that is this. There was a constant increase of 50 cents each year. So the constant change was increasing. So also plus 50 cents each year. Yeah, pattern. Put a period. Compute the slope. Well, we could do this two different ways. We could say this: what is the change in the response variable, 50 cents, compared to the change in the explanatory variable, which is 1 year? So the slope change in response, this ratio compared to the change in explanatory. Okay, so the ratio of the change in response compared to the change in explanatory increased by 50 cents. So change of positive 50 cents and per 1 year. Got it. Is the graph increasing or decreasing? Well, it's increasing. How can you tell? Well, two ways. It goes up. Okay, so it goes up as we read it from left to right. Okay, as we read the graph. Also, I mean, the slope tells us. So plus 50 cents each year. So the ticket price is increasing. It's been getting more expensive at a rate of 50 cents per year. What is the initial price of a ticket? Well, it says it was originally $1 in 2010. Initial price of a ticket, $1 in 2010. What is the pattern from the table? Plus 50 cents, plus 50 cents, plus 50 cents. Plus 50 cents. Okay, so we know it's linear. Write an equation that describes the relationship between the price of the ticket and the time passing. Okay, we got to give some variables here. Let's go t equals years. You cannot see this. Years since 2010. Let's call the price P. Price of a ticket in dollars. And then, okay, well, it started at $1 and then we are adding 50 cents however many times per year. So like we start at $1 and then we add 50 cents. Started at $1 and then we added 2 additional 50 cents. Started at $1 and we added 3 50 cents. So the way I'm thinking about that is like this. The price is equal to $1 plus 50 cents is added t times. So here 50 cents is added no times to the buck. Here 50 cents is added 1 time to the dollar. Here 50 cents was added 2 times to the dollar. In 2013, 50 cents was added 1, 2, 3 times to the dollar. Okay, so I'm interpreting that into an equation here. The price is equal to $1 plus 50 cents added t times for each year. Okay, in the next example, we will look at depreciation, or writing a linear equation for a situation that has a rate that's going down.